the regular solution model was a hybrid of two things. First, we took for the entropy of mixing, we took the ideal solution entropy. And I've written it out here just for a binary. So what I've written out is the minus T delta S of mixing term. And we then also calculated the enthalpy of mixing with a very simple bond model, right? We gave AA bonds and energy, BB bonds and energy, and AB bonds. And we found that if you then assumed that the bonds were the atoms were randomly distributed, you could calculate the probability of each bond, and that led us to a quadratic for the enthalpy of mixing, okay? And so this is what's called the regular solution model. Again, it's still a model, but it shows the first sort of level of complexity that we can do something useful with in phase diagrams. But of course, in reality, free energy of mixing can behave quite a lot more differently. So I want to discuss the energetics. I want to discuss two cases, depending on whether omega is positive or negative. So when omega is negative, right, then the enthalpy of mixing term is negative. So you have what is referred to as exothermic mixing. And that makes sense if you think back of what omega is. Omega had a bunch of constants in it, but omega was proportional to the WAB bond energy minus the average of the AA and the BB one. Right? So omega was proportional, and there's some other like Avogadro's constant and so in there. But so what you see is when omega is negative, that means that the AB bond energy is lower, so it's more cohesive than the average of the AA and the BB bond. So when you mix, that means your system goes to lower energy because it replaces some AA and BB bonds by AB bonds. And that, of course, is what the exothermicity is, right? You're actually releasing energy as you form the compounds. In case 2, omega is positive. So that means that delta H of mixing is positive. So you will have endothermic mixing. And again, that makes sense because now you're actually going to a higher energy bond. If omega is positive, then the AB bond is higher energy. And so you actually have to add energy to create the mixture, okay? And so you may think that in principle, this would never happen, omega positive, because the thing wouldn't mix. But remember that you always have the entropy term, which always favors mixing, right? Because this term is always a negative contribution to the free energy of mixing. So what I want to talk about is in a little more detail of how the free energy curves look like for omega positive and omega negative. But first I want to pick up the question that I asked in parting last time, is that this model is sort of internally inconsistent, and that will determine where it is more or less accurate. And why is it inconsistent? Because so we developed these terms, both of the entropy and the enthalpy term. We developed under the approximation that the system was completely randomly mixed, right? What sat on a given side was a completely random outcome. But on the other hand, we gave the system energetics, right? We gave it a certain bond energetics. So let's say I'm in the case where omega is negative, right? So in that case, what's here in blue is negative, so AB bonds would be more preferred. So in that case, if I were to have a configuration like this, say where I alternate, A and B bonds, that would be much more favored than, say, something where I phase separate them. So let's say I make two configurations on the lattice, right? This one, you know, let's call it configuration 1, would have a lower energy than configuration 2, so configuration 1 would have a higher probability. So this is the problem with the regular solution model, that it gives the bonds energetics, and therefore your system has energetic preferences. But when it actually does the math for the entropy and for the enthalpy, it doesn't take that into account. It still assumes that you have a random solution. And so when will the regular solution be better? Well, it will be better when this actually does become random. And that's at high temperature, right? Because if you calculate the ratio of two configurations, Pi, Pj, the reason I do the ratio is because then the partition function drops out. That's the exponential of minus beta EI minus EJ. So in general, when EI and EJ are not the same, this probability ratio is different from 1, but of course, when beta goes to 0, then the ratio of Pi, Pj becomes a constant and actually becomes equal to 1. And beta equal to 0, it means T equals to infinity. So what you can deduce from this is that the regular solution model is truly only internally consistent at infinite temperature. Okay, so what's the farthest away from infinity? I guess that's 0, depending on your math world. And so at 0 Kelvin, you should be careful with this model, and I'll show you a few, or as you approach low temperature, you should be careful with this, and I'll show you a few cases of that. And of course, what does low temperature mean, right? When we talk about low temperature, it means low on the scale of the energetics, right? If you have a very large energetic parameter, then of course low temperature can actually be high temperature, right? So it's whatever is low on the scale of omega. Okay, so let's look at what kind of behavior this model gives. And I'll first start with the omega is negative case, because it's the most obvious one. So if you plot the free energy of mixing by its contributions, so then in this case, the enthalpy term is negative, right? And remember, the enthalpy term is a quadratic, so this would be the enthalpy of mixing. The minus T delta S term is always negative, but remember that that one looks different because it has these infinite slopes. It's sort of hard to see on a graph that it looks different, but remember, enthalpy does not have any infinite slopes. There's no reason for it to have it, but the minus T delta S term does. And then of course, the sum of the two is the free energy of mixing and this is negative and convex everywhere. So according to this, the regular solution model predicts perfect mixing at all temperatures. And of course that can't be true, right? Because that violates the third law of thermodynamics, that we have to go to a state of perfect order, that we cannot have entropy at 0 Kelvin. So we'll see later what kind of goes wrong with that. But before I do that, I want to develop in more detail the omega positive behavior, which is a little more interesting. So when omega is positive, the reason it gets more interesting is because you have competition between the enthalpic term and the entropic term. So in this case, the enthalpic term is positive, but the entropic term the minus T delta S term is always negative. I apologize for my drawing here. And so now what actually happens depends on the magnitude of T. So you can already see if T is very small, then your free energy will look mostly like delta H of mixing. If your T is very large, then it will look like minus T delta S of mixing. But in between, it has interesting behavior, and that has to do with the slopes. So the minus T delta S term has negative downward slope here, whereas the delta H of mixing has finite positive slope. That means that for any T, the free energy curve starts off going downward for any temperature. And this is important because when T is small, at some point I have to basically get the delta H curve back, right? So at some point this actually has to go back up. And it does something like this. This isn't quite done well to scale here, but you see the point, right? For any T, delta G of mixing starts off going down, but if T is small, then in the middle it has to sort of look like the delta H of mixing. And so now you get a curve that has non-convexity in it. Which means that you have sort of interesting behavior going on. Let me pick that up here. We sort of went through that in part, but I'll sort of, because it's so important, let me do this again. So when you have a free energy curve that looks like this, so this is delta G of mixing. Even though that free energy curve looks like it, well, it doesn't look like it's negative. It actually is negative everywhere, which means that there would be an energy lowering when you mix. Right, since I'm plotting delta G of mixing, before mixing, let's say I make this composition here. Before mixing, my energy of mixing is 0, of course. And then when I mix homogeneously, this would be my free energy of mixing, so that would be the lowering of the free energy. But what you remember from the chord rule is that I can keep on lowering that free energy, right? Because in this case, I can unmix. For example, if I tell you I unmix this as a solution, I'll call this XB prime, and I'll call this XB double prime, right? If I unmix this system, so I make XB prime, XB double prime, and let me call the total XB, so the overall composition XB star. So the total here has to be XB star. And remember from the lever rule or the chord rule, you can figure out how much there is of each. So what's the free energy now? Well, now the free energy is given by the chord. Right, so by unmixing, my free energy actually goes down. And you can see that I can keep on doing this until I get the lowest possible chord. And the lowest possible chord is what's called the common tangent. And I didn't do my drawing right because in the regular solution model, the system is symmetric around 0.5. So let me redo this, which I'll say a few words about in a second because it's a bit of an aberration. So if the free energy curve is symmetric around 0.5, then the common tangent has to be horizontal. So this is the lowest possible chord. So the lowest free energy that I can reach is this point. And that's when I phase separate into, I'll call it XB1 and XB2. So the ultimate equilibrium state is phase separation between XB1 and XB2. And I'm sure a lot of you have seen this sort of in undergraduate, right? This is what you call the common tangent, but you get there also by considering the chord construction. Note that this also satisfies equilibrium, which the intermediate chord didn't, right? Because if I take, let's say I call this side alpha and this side beta, just to distinguish the two phases. What's the chemical potential of B in alpha? Well, remember it's the intercept rule, right? So I take the tangent. So this here is the chemical potential of B in alpha. And in equilibrium, that should be equal to the chemical potential of B in beta, which is true because they share a common tangent. So if I take the tangent in this point, phase 2, phase beta, I get the same common tangent. So this is also the chemical potential in beta. And the same for the A side. Right, so you know that if you have two phases in equilibrium, they have to be connected through a common tangent. The compositions of the two phases, right, have to be in a point on the free energy curves where the tangents are the same. Otherwise, I cannot have the same chemical potentials. I want to say something about this construction because I like explaining this by the regular solution model, but there is sort of one failure of the regular solution model that's really annoying. Because it's symmetric, the regular solution model, the common tangent points are in the minimum, right? Because the common tangent has to be horizontal, but in reality, I've never seen in my life a symmetric free energy curve of a real system. So in reality, it looks something like this, right? So very asymmetric, delta G of mixing. So if I draw the common tangent now, so if I have some overall composition here, so now of course the common tangent is not at all, it's a bit of a bad drawing, but is not at all horizontal, and the equilibrium concentrations are not at all in the minimum of the free energy. If I were to ask you, why does this not make any sense? So, well, maybe I should rephrase my question. What is the physical meaning of the minimum in the free energy curve? If I plot a free energy or a free energy of mixing, kind of same thing, right? They're a different reference state, as a function of composition, what is the meaning of the minimum?
That adding material to the phase doesn't change its free energy.
That's sort of a mathematical translation, right? But
that's how I got there, yeah.
But is there a physical meaning to it? It's a trick question, right? So the answer is no. There is no physical meaning to this minimum. And the reason is that this is a curve of G as a function of composition. But G is only minimized for a closed system. So this is not a relevant potential as a function of composition. This is a relevant potential at a given composition, but not as a function of composition. So the minimum is completely and utterly meaningless. And I'll show you that prove that to you in a second. And the reason I say that is because I always get 2 or 3 students on the exam who do something with the minimum. If your answer is the minimum, it is unlikely to be correct unless we accidentally deal with a symmetric curve. And let me prove that to you. I can change the reference on the A and the B side, right? I can add like, you know, plus 500 joules here or kilojoules here. And that's just changing the reference energy for B. That is the same as adding a linear curve to the free energy. And a linear curve shifts where the minimum are, right? Because the minimum is where the derivative of dg, dxb, is 0, right? That's the minimum. If I add a linear piece to the free energy, then suddenly this becomes some linear piece. The same point. So it has no meaning. The minimum where the minimum is in the free energy curve depends on the reference state. Okay? So keep that in mind. So what we've shown here is that the equilibrium here, when omega is positive, is a little more complicated. There's essentially 3 domains. So here you have single phase alpha. Here you have single phase beta. But in between, the lowest energy state is a 2-phase region, is alpha plus beta. Some people on your qualifier won't like it that you call these 2 different phases, alpha and beta, because they live on the same free energy curve. So some people, some books you will see call them alpha and alpha prime. I couldn't give a whit. When they live on the same free energy curve, it usually means they have some structural relation. So what do you think now happens to these solubility limits, the edges of the 2-phase behavior, as you change the temperature? Right? So let's think through that. When T becomes smaller, then the minus T delta S part becomes smaller, so you're going to be more dominated by the delta H part. On the other hand, if T becomes larger, at some point T will be large enough that you should have mixing in all proportions, because for some very large T, the free energy curve is just going to look like the minus T delta S curve. Okay, so let's do a very low T. So let's go lower T. Sorry, I need space for my enthalpy. So you will have a delta H. Try to keep the same colors. So now minus T delta S will be very small. Which makes it hard to draw. And then the free energy curve will essentially come down and almost immediately rise. So in blue here will be delta G of mixing. And that means that the common tangent points, because the free energy curve turns up very soon, will be very close to the pure axes. Right, so you will have a small domain of alpha, a small domain of beta, and a very large domain of alpha plus beta. On the other hand, if you go to very high temperature, you become totally dominated by the entropy term. So let's do really large temperature. So now you have minus T delta S of mixing here. So delta G just tracks this basically. And now you have mixing in all proportions. So let's put that together on a phase diagram. So a phase diagram will now put that together, these solubility limits, as a function of composition and temperature. And so at low temperature, they will be small. They will go up with temperature. And at some point, there will be complete solubility. And so the phase diagram will look like this. Here you will have solid solution. And here you will have 2-phase behavior or unmixing. And that's why this is referred to as a miscibility gap. A miscibility gap isn't a particularly well-defined thing, but it's everywhere where a 2-phase region does not exist. And again, remember how to read this. It's called two-phase, but I'm going to erase it so I can actually do something else in it, but it's not an error. It is two-phase. So remember what a two-phase region is, right? If you are sitting in a two-phase region, a two-phase region is like a hole in the phase diagram, right? If I could punch out the board, I would punch out the miscibility gap. Because really, what the thermodynamics is telling you is you cannot exist in there, right? The thermodynamics tells you fundamentally that you don't exist in here because it is better, it is lower energy to make two phases, one with, say, if you're at this temperature, one with this composition and one with that composition. So phase diagrams are super easy to read if you fundamentally think differently of single phase domains and multi-phase domains, right? A single phase domain marks the existence limits of a single phase. Everything else is a whole. Everything else you have to make up by making other phases coexist. So if you want to make a composition in here, you cannot do that homogeneously. You have to make it up by making a phase of that composition and a phase of that composition in the right ratio. I want to show you quickly that there are plenty of systems that actually do this. Okay. So I picked out a few very basic systems here. For example, here's the gold palladium system. These are, the reason it's simple phase, and these are both FCC solids, and they make this sort of beautifully almost symmetric, oh dear, almost symmetric miscibility gap. Often this is labeled as sort of, this says gold plus platinum, but of course what they really mean is a gold-rich solid solution and a platinum-rich solid solution, right? But sometimes the nomenclature is a bit annoying. Here's chromium tungsten, that's a BCC miscibility gap, because here's is a BCC solid solution, and at lower temperature you have a miscibility gap, okay? So that's the case of omega positive. What you have to take away here is that when omega is positive, the enthalpy favors unmixing, right? Which means at lower temperature, indeed, you don't want to mix. But the entropy, of course, always favors mixing because you make more states when you mix. And so there's a temperature where the entropy wins, and that's where you become a solid solution. Let me now do the case of omega negative. Because the regular solution approach cannot be correct there. So if omega is negative, then in the regular solution model, WAB is less than WAA plus WBAB over 2. And as I showed you in the beginning, regular solution would simply predict that you mix at all temperature and in all proportions. That's because it's the best it can do given its assumptions. But what will really happen is that, of course, what you will want to do at low temperature, you will want to maximize the number of AB bonds, right? For example, let's go down to 0 Kelvin, where we don't have to worry about the entropy. Really, to get the lowest free energy, you just want to make something that has as many AB bonds as possible. And this is what is called compound formation. So the atoms will order in a pattern that maximizes the AB bond formation, or technically more correct, that minimizes the enthalpy. So the correct statement is that when omega is negative, you get compound forming or ordering. You can actually, you cannot directly from the regular solution model build a free energy model for a compound, because remember, the regular solution model started with the wrong assumption. It started with the assumption that everything's randomly mixed, and a compound is exactly the opposite. In chapter 5 in Gordon, where he talks about order disorder, Gordon shows how you can extend the regular solution model by doing regular solution on distinct sublattice and how you can model compound forming like that. We're not going to do that in class since we don't have time, and it's also a bit old-fashioned. But I just want to give you a sense of what happens in terms of free energy curves. So if you have compound formation, the way we think of that is that you have a different free energy curve for a compound. So let's say I have a solid solution free energy curve. All right, so let's say this is delta G of mixing for the solution, so the homogeneous mixture. Then at some point, a compound, let's say let's do it at 50-50, so, we have AB composition. So a compound will have lower free energy. So let me give this thing a name. I'll call this gamma, since I've already used alpha and beta. I've drawn this in a particular way, and sometimes I get questions, why do I draw this steeper for a compound? The reason is that in a compound, often going off stoichiometry comes at a high energy cost. So that's why the free energy curve often has a much steeper shape. So how would a phase diagram of this look like? If I can find my pens here, my colors. So again, you can draw a common tangent, right? So here's a common tangent. Here's a common tangent, very badly drawn. Okay, so what do we have? We have a bunch of two-phase regions. So here I have alpha. If I call the compound gamma here, I have alpha plus gamma. Here I have pure compound gamma. And then here I have gamma plus beta if I call the other phase solid solution beta. So I have alpha and beta solid solutions, right? So pure A with some B, pure B with some A here. I have the compound, and I have two-phase regions between them. By the way, do you see that whenever two free energy curves intersect, I will always have a two-phase region in between? If I in a composition axis, if I have two free energy curves, it doesn't really matter what they are, I will always have a two-phase region in between, right? Because they intersect with different slope. And that's why later when you look at phase diagrams, you will see that almost always between single phases, there's always a two-phase region in between. And that's just because of the nature of the intersection. And so we see the same here. So let's imagine now what would happen to this as a function of temperature. So this is something you have to kind of learn to think. You have to learn to think like a free energy. So if I, if I raise the temperature from this picture, right? Let's say this is at some temperature, and I increase the temperature. What will happen relatively to these free energy curves? How will they shift relative to one another? The way to think about it is, right, what's the derivative of free energy with temperature? Right, it's minus S. Right, so the thing with the largest entropy, if I raise the temperature, that thing with the largest entropy will come down more. So what's the thing with the largest entropy? It's the solution, right? It's the mixture. So if I go down to higher temperature, what you think about, this blue curve should start coming down, or you could think of the black curve going up. So as the temperature goes up, this black curve will start to move up or you could think of the blue curve going down, and at some point it will just touch there. Again, this is the solution. Then at some point, the free energy curve will just touch there, and after that it'll disappear, right? If I go even higher, the blue curve will come down even more corresponding to the black curve, and there will be no region of stability anymore of the compound. So if you put that all together in a phase diagram, so now I'm plotting T versus XB. Let's say I have a single compound at AB, I will have some domain of stability of the compound, which I'll call gamma, and then there will be sort of a two-phase dome over it. Here I will have solid solution. Here I'll have alpha. I'll call this side beta, again with the caveat that some people don't like that. Here I have alpha plus gamma. Here I have gamma plus beta. So what do I want you to know and understand? What I want you to understand is, like, when you look at these phase diagrams, I want you to think like a free energy. I want you to understand where they come from, how they come from, why they are logical when you start thinking of relative free energy shifting with temperature and composition. So when you see a free energy curve, when you see a phase diagram, you should be able to draw a free energy curve. If you get free energies at one temperature, you should be able to extrapolate behavior to other temperatures, depending on what the estimated entropy of each species is, right? So you should be very flexible going back and forth between free energies and phase diagrams. And that's sort of the extra step we make here, right? And we'll do a lot more of that. That, you know, as a freshman or whatever, you learn to read free energy phase diagrams, like you learn to read them like they are maps. We're not trying to sort of understand the underlying behavior of what creates them.
Why at the very bottom of that phase diagram did you bring the gamma to a point?
Oh, here?
Yeah.
Yeah, because you can actually not, so you cannot create disorder because you would be creating entropy. But the other reason you could think about it is that there is no benefit to creating disorder because T is 0, so the entropy term does not contribute to the free energy. So assuming that this is the optimal solution for your energy problem, right, that is at one given composition, that will be the lowest free energy. Everywhere else, the free energy will go up. Okay?
Okay, thank you.
And so, by the way, this is something you find in any real system, that all phases come down to a single composition if you go down to 0 Kelvin. Of course, in experimental phase diagrams, you won't always see that because they measure them up to a certain temperature, and after that, the kinetics, flips out, and you can actually not equilibrate them down to low temperature. But they always come down to a point. So most of the phase diagram at 0 Kelvin is made up out of two-phase regions. Okay. Let me show you a diagram like that. Okay, here's a sort of slightly more complicated one. There's more than one compound, but this is copper palladium. And this is next to it is copper gold. And basically what you have here is you have sort of, these are compounds, all these single phase domains here that you see. It's a little hard to see. And then here you have solid solution. So this is a slightly more complicated case, but it's essentially a sign of omega negative. Same here, because you have compound formation. sometimes sometimes you will read that there are 3 types of phase behavior. There's unmixing, there's compound formation, and there's solid solution. But let me argue that that's not correct. So we've seen 2 cases so far, right? We've seen what is characterized by omega positive, which is the miscibility gap. Right, so here your solid solution. And then when the interactions are different, you have compound formation. And you know, in most real phase diagrams, you will have multiple compounds. I'm just doing one here to make it simple.
Could you unshare your screen, please?
Did I what? Oh yeah, thank you.
Thank you.
Sorry about that. Okay, omega positive, we have 2 phase. Omega negative, we have compound formation. And my argument is that there are only 2 cases in nature, because the 3rd case, solid solution, is the high temperature version of each of them. So solid solution, or you could think of it mixing in all proportions, is not a real physical case. You have it in both cases if you go to high enough temperature. So both the omega positive and the omega negative case display solid solution if you can just go to high enough temperature. So the important takeaway here is that, let me hold the important takeaway. I have to tell you something else first. Suspense. So if you are here at this temperature, and let's say, you know, if you go lower in temperature, the system becomes hard to equilibrate, so it becomes hard to figure out like what phases there are. At these temperatures, you will see solid solution in both cases. How do you know what's coming at lower temperature? How will you figure out whether this is omega positive or omega negative type system? And I'll tell you, sometimes this is important because sometimes people worry about, like, they still need to know the behavior for reasons that I'll explain later. Or sometimes you just want to know what it's going to do over the long term. Like, you know, if you let the thing sit for years, will it order, will it phase separate? This can be very important for the stability of materials. So how would you figure that out? The question is, really, are there other signs? If you're in the solid solution, are there other signs of whether you're here or here? And there are, right? So the first thing is you could just measure the enthalpy of mixing. If you measure the enthalpy of mixing here, the enthalpy of mixing would be negative. So you can just do that with a colorimeter. And here, the enthalpy of mixing would be positive. And the enthalpy is probably the most fundamental property to measure. But there are other ways you can measure this. You could measure the short range order. So you could measure short range order, which is a lot harder to measure. You'd have to do TM or neutron diffraction or something like that. But here, you're gonna, if you measure short range order, here the probability to find AA bonds, for example, would be larger than XA squared. Right? XA squared is what you would find if you're random. If you're larger, that means your AA and BB bonds are preferred. And here, the probability to find AB would be larger than, sorry, the probability to find AA, let me do it that way to keep it simple, would be less than XA squared. And actually the easiest way, but also the least accurate way, is to look at the lattice parameters. So you look at the lattice parameters as a function of composition. In a compound forming system, because AB bonds want to form are favorable, tend to contract the system slightly. So in a system like this, if you plot the lattice parameter as a function of xb, so now we're plotting like A stands for lattice parameter. So let's say it has a value in A and it has a value in B. Vegard's law, which is linear interpolation, would be this. In reality, you will often have slight bowing out, bowing down, because essentially the system wants to be together. It wants to be mixed. In the other case, in the omega positive case, you would have positive bowing. It's the easiest rule. It's also the one that it holds the least. It's, you know, it holds very well in metallic systems. It doesn't really hold particularly well in anything else, like it wouldn't even hold particularly well necessarily in oxides. But this one is the one that's always true and is the most fundamental. So now I'll come to the takeaway. The takeaway is that in the world, there are only two types of thermodynamic systems. There's the ones that have positive enthalpy of mixing, and there's the one that have negative enthalpy of mixing. And this is actually the fundamental quantity. We got there by going through the regular solution model and talking about omega, but omega is really only a representation of what really the enthalpy of mixing does. So if the enthalpy of mixing is positive, you want to phase separate at low temperature. If the enthalpy of mixing is negative, you're a compound former. That's all there is to thermodynamics and phase diagrams. There are only two cases, nothing more. And if you know the enthalpy, you can sketch a prototype phase diagram. Okay. Let's now introduce what happens when you bring in the liquid. So if you remember, we've already talked about liquid solid phase diagrams, right? If you remember a while ago, we derived the two-phase equilibrium when both liquid and solid are ideal solutions. If you remember that, if both liquid and solid are an ideal solution, you got a lens type diagram. I also derived the other case when the liquid was an ideal solution, so mixes very well, but the solid was non-miscible. And in that case, you had melting point depression. So let me first do the case. So we're going to add the liquid. So case one is where the solid energetics, all the behavior in the solid, is well separated from melting. What I mean by that is that, you know, whatever goes on in the solid, whether you form a two-phase region or a compound, kind of disappears by the time you get to the melting point. So that means that the solid will be a solid solution. So basically, you will just be adding a liquid lens to this, right? So here you have liquid plus solid, and here we'll have solid solution. Right, because by my definition, by my statement, I'm saying, well, there is some kind of low temperature energetics, which makes a miscibility gap. But I get to high enough temperature where the thing becomes solid solution. And so my interaction with the liquid will very much now mimic what two ideal solutions do. Because the solid can actually mix already by the time it hits the melting points. And same here, right? So in this case, the phase diagrams are essentially superposition of two items, right? What we've developed for the low temperature and what we've developed for the liquid. And the phase diagrams that I showed you before, which I guess I could show you again, but I'm not going to do because I have to switch screen again. The copper gold one, the copper palladium one, the chromium tungsten one, the gold platinum one were essentially all those kind of phase diagrams. You had a low temperature feature, and then you had a lens type diagram. Okay, actually I do want to show it to you because I want to show you something. Okay, so this is sort of what I mean, right? So for example, chromium tungsten here on the right-hand side, you have a miscibility gap, you have enough region of solid solution here, and then you have a lens, and you know the lens is a little bit distorted, but looks like, very much like a lens. On the left, the gold platinum, they get very close together here. And that's actually what makes the lens quite distorted, right? But still looks like a lens, right? It doesn't really look like a melting point depression. And here you see that for another system, this is a copper nickel. Again, usually categorized as a solid solution because it actually is a low temperature miscibility gap. But if you look, the temperature of the miscibility gap is about 200-300 degrees. And so it's very hard to actually see it because your kinetics gets very poor. Here's some more. This is a lens in copper palladium, where again you have low temperature features and then a slightly deformed lens. And in copper gold, it starts to look a little different already. Again, you have sort of this low temperature features. You still have kind of a lens at high temperature, but the lens is starting to be seriously distorted. It's actually pulling down here, which is probably indicating some issues with solubility in the solid state. Okay. So what I want to develop now is what actually happens when these things run into each other. So when the energetics in the solid is on the scale of the melting energetics. So the temperature at which the sort of energetics of the solid disappears is near or well above the melting point. So all these things run into each other. Okay, so the sort of idea is that, let's say I draw the beginnings of a phase diagram. You know, you have, say, melting points. So this would be Tm of A, Tm of B. And let's say I had a low temperature miscibility gap. And if I were to sort of draw that metastably, it would go way up there. So it has to run. So this would be like a miscibility gap. It would sort of run way into the melting behavior. So the question is, how do you connect all this stuff together? I think many of you know the solution, but I want to show you that there's really just a very systematic and logical way that this all falls into place. So what we're doing now is solids with low solubility up to the melting point. That's really what this means, right? I'm not getting a whole lot of mixing up to the melting point. So let's get there logically with free energy curves. So let me first do low temperature, where the only relevant stuff is what goes on in the solid. So I have some free energy curve of one solid on one end, say, and I have some free energy curve of another solid. They have a common tangent between them. So this is the common tangent. And then maybe there's a liquid in play, but the liquid is way too high in free energy to ever play, right? So let's say this is the liquid. So the liquid is never low enough to be the lowest energy state. So what's the phase equilibrium? You have alpha here, you have alpha plus beta here, and you have beta here. Okay? So let's now think about how the system evolves with temperature. So this is the low temperature behavior. What happens when we raise the temperature? Think about it, right? You should learn to think like a free energy, right? I go up in temperature. How do these curves slide with respect to one another? So just what you want to think about, what has the highest entropy, right? What has the highest entropy comes down relative to the other stuff. So I'm going to keep sort of alpha and beta in the same relative place. But what happens to the liquid? Right, the liquid has the higher entropy because it's the higher temperature phase. So the liquid will move down with respect to the solids. And at some point it moves down and it meets the tangent, right? So I'll draw the point where it meets the tangent. And the tangent, when it meets the tangent, is just the moment of anticipation, because what you're really anticipating is when it comes through the tangent. I'm going to draw here. So now we go even higher temperature, right? So we increase T even more. And so now this is the liquid. So what do we have now? Well, now our lowest free energy surface is made up out of two tangents, right? There's one here, alpha, alpha plus liquid. And I have liquid here, and then there's another tangent here. So I have liquid plus beta, and I have beta. I'll give you a moment to take that, and I'll try to keep it in view, yes, while taking my coffee. Okay, I hope you're with me, right? That this is all very logical. All I've said is I have two phases with limited solubility in each other here. I have a liquid, and with temperature, they have to move like this, right? Do they have to move like this? You never question me, right? Does a liquid always have a higher entropy than a solid? Anyway, we're going to defer that to a few lectures from now. But think about this. A, is there a principle in thermodynamics that tells you that the liquid should have higher entropy than a solid? Is there such a principle? And B, how would the world look like if the liquid can have lower entropy than the solid? But take that home, okay? Not now. Well, you are home, sorry. Take that to your next coffee break. Okay, so how's the phase diagram of this going to look like? So let's do the phase diagram now. So at low temperature, I just have solubility boundaries. right? So here I have alpha, here I have beta, and here I have alpha plus beta, right? At high temperature, I have 3 single phase regions, alpha, liquid, and beta, and 2 two-phase regions. So at high temperature, I have something like this. I have liquid, I have alpha plus liquid, I have liquid plus beta, and I have beta. And then at some point in between, which is this point, I have 3 phases which I can combine in any linear combination and always get the same free energy, right? This is the cool part about this, right? If I take any composition here, I can make this free energy here, if this is my XB star, I can make up this free energy by any combination of liquid and beta, alpha and beta, whatever, right? So how do you connect this? Well, you basically just extend these, right? And you know how this is going to look like. This looks like what's called the eutectic phase diagram. Oh, it's a very bad drawing here. Okay, looks approximately correct. And now we can put our temperatures on here. This is T1. I'll call this TE for T eutectic, and this is T3. So this here is T3. This here is TE, and this here is T1. Okay, let me show you a few eutectics. Now that you've seen that it's the logical outcome of phase diagram curves. And as you can kind of imagine, this should be much more common than the case I showed you before, right? Because we just don't often have very good solid solution in the solids. So this case where kind of the solubility in the solid state runs into the melting behavior is actually much more common. Okay, so here's a fabulous eutectic. It's the copper gold system. If you don't know how to read a phase diagram, you should, we'll put a reading online if you sort of, you know, if you don't have a material science background, if you've never read phase diagrams, you want to make sure you get up to speed on that. It's not something we're supposed to do in this course. But, you know, let me tell you, if you're a card-carrying material scientist, you kind of have to know your phase diagrams, okay? It's like one of the worst ways to get embarrassed in a meeting or in a qualifying exam or something like that. So again, so here's copper gold, right? So here's solid solution, which is mainly copper rich, right? Here's a solid solution that's mainly silver rich. And then here's the liquid, right? So there are only 3 single phases present here. And then you have a bunch of 2-phase regions, alpha plus beta, alpha plus liquid, and beta plus liquid. Again, the way I would think of this is the only regions that you care about is these guys. Because they are the only regions where something exists. Everything else is a whole. So I used to, when I was teaching undergrad thermal, I made a phase diagram like this in cardboard, and I would punch out the 2-phase regions because they are regions of non-existence, right? So really, you cannot exist here, okay? You have to make this up by phase separating into this and that. Okay, very quick rundown about how you cool through a eutectic, but if you don't get this, you should ask the GSIs in discussion section. So let's say you start here maybe I should take another color because too many colors. Green, let's do green. You start here. If you cool down, you hit the two-phase region. What happens in the two-phase region? You, once you enter the two-phase region, you make solid with this composition. And the liquid is this composition. If you cool down, I can remove this. If you cool down, let's say you're at this temperature. So now you have liquid with that composition, solid with that composition. So basically the liquid tracks this composition as you cool, the solid tracks that composition. So when you're sort of say up here, your material would look something like, you know, you would have solids, sort of call them alpha, right? Maybe floating or sticking to the container, and most of it is liquid, and the liquid would have this composition. So I'll call that X liquid, and the solid would have this composition. So you have X solid, and here you have X liquid. And you can figure out the lever rule to figure out how much of each phase you have. So you should know this, right? This is undergraduate stuff. So if what I'm talking to you or showing to you looks like complete, like, I can't say Chinese because some of you speak Chinese, Greek. If some of it looks like Greek to you, because nobody speaks Greek, cool, okay. You should read up on this, right? Because you don't want to like mess this up. The unusual thing about a eutectic is of course that once you hit this point, so the eutectic temperature, why my pen, bad pen. When you hit the eutectic temperature, you have liquid with that composition and solid with that composition. And when you cool down further, that liquid has to decompose into two solids. So below the eutectic temperature, there is no liquid anymore. Okay, let's see if I can do this. I'm sorry, I'm going to have to switch back and forth between the board and the slides a few times. I asked if anybody of you spoke Greek. That was intentional because eutectic is a Greek word. And I'm not going to impress you and write eutectic in Greek. It's eutectai, which I think is that. So this is Greek for eutectic. And eutectic means to melt low. And of course, that is the cool thing about a eutectic, right? That there is a point here where the liquid melts at lower temperature than pure B or pure A. And this is what we talked about before, that because of the poor miscibility in the solid, you have a general melting point lowering when you mix things. And you see that on both sides here. So at some point they meet and you have the lowest possible melting point. And this is of course technologically of tremendous importance, right? But I hope you understand the physics of where this comes from, right? It's because you really have a hard time mixing. So let me show you a few famous eutectics. Apologies for the back and forth. If I ever have to do this again, which I hope I don't, I will set up something faster. Okay, lead tin, right? Famous eutectic because of course this is the original solder. Lead melts at 327 Celsius. Tin melts at 232. But hey, if you mix them together in exactly the right ratio, and the right ratio is about 2/3 tin to, 2/3 tin to 1/3 lead, you have something that melts at 180. And this matters a lot, like this difference, right? You know, you're down like 50 degrees from pure tin, so you don't have to heat solder as high. And if you've ever seen soldering, by the way, solder is not lead tin anymore today, but if you've ever seen, like some of you may have soldered with a soldering iron, right? Where you kind of heat the thing up and you put solder in. But the way electronics is soldered is, of course, that they put everything through a circuit board and they dip the circuit board down into liquid solder, and capillary forces pick up a solder bubble, and that basically solders the whole thing. But you really want to keep that temperature low because your electronics is, everything on your printed circuit board is exposed to the temperature. The plastic, the circuitry, and you know, for plastics, 50 degrees around this temperature means a lot, right? If you stay below 200, there's a lot more plastics you can use than if you like have to go to 250. Of course, we don't like lead anymore because we're environmentally conscious. We don't like lead anymore. Oh, but first, by the way, what do we replace lead with now? What's in solder now? Is there still lead in the solder? Not if you're in the European community. The EC has banned all lead solder, and it's basically kind of done in the US too, and pretty much everywhere. So what is solder now? Unfortunately, this was the best one. So, but basically now people use mixtures of, so it's still tin-based, but then they typically add things like silver or copper, antimony, bismuth, basically a bunch of other things. But unfortunately, nobody's gotten it down as low as 183. So commercial solder now is a little higher, but we've gotten rid of lead, which is good. There is still lead though in some solders. Does any of you do plumbing? Plumbing is a great skill. Here's why you should learn to plumb, because you can always fix your own plumbing. And plumbers are expensive, right? You know that plumbers are called the kings of tradesmen, right? Because they charge the most, they come in first, they make everybody else work around them. They make the most money of typical tradesmen. And you always need them in a hurry. That's the other problem, right? So you should learn to do plumbing. So plumbing solder sits here, roughly, in composition. Why not in the eutectic? Because if you're a smart plumber, you know, so plumbing you do with a torch, right? Propane torch, or by the way, which is also good for making creme brulee. You can actually, you don't have to buy the fancy, like, you know, from the fancy store. You just get a plumber's torch and you can make creme brulee. But why is plumber's solder basically more in this compositional direction? Well, what do you think, right? First one is cost. Lead is a lot cheaper than tin, right? Tin is actually multiple factors more expensive than lead. But the other one is that, has any of you ever done electronic soldering? Plumbing and electronic soldering are fundamentally different. In electronic soldering, you want the contact to solidify instantly. Because if you ever notice, if you move it while it's solidifying, the solder doesn't look shiny anymore, and you get this, it's because you get a very weird microstructure which is very prone to fatigue. And a eutectic is great for that, because a eutectic, basically at one temperature you solidify. So as soon as the temperature drops, you're done. Plumbing solder is different, because when you do plumbing, you actually solder the joint and you want to be able to twist it. So there's something that they call the mushy zone, and the mushy zone is when you cool through the two-phase region. So in plumber solder, you don't want to have instant onset of solidification always. So you actually don't want to be in the eutectic. But the main reason is really cost, okay? We actually don't really like lead in our drinking water either anymore. So sadly, lead had to go. Well, you know what we use now in plumbing solder? I don't think it's much better now. It's antimony. And antimony is not that good for you either, but it seems to have never gotten on the blacklist as much as lead does. No, lead is bad for you. Don't let me say anything else. So, okay. I think we have time for one phase diagram, right? Oh, my favorite. Water ethylene glycol. What is this? You know that, right? I know you live in Berkeley. Well, now many of you don't. You don't have a car. You're conscientious. But this is what you need if you have a car. Maybe not in Berkeley. Anybody here from a cold place? How cold?
Michigan.
Yeah, cold. Very cold. Okay. So this is antifreeze, right? Water plus ethylene glycol. This is what you put in the radiator of a car so that it doesn't freeze. And I'm going to tell you a good story about this, and this is a true story. There were days where, you know, we would toy with cars with my friends when we were very young, and we would replace antifreeze, etc. So antifreeze is essentially water and ethylene glycol. And, you know, water, you know, freezing point is 0 Celsius, right? And the perfect ratio is about 2/3 ethylene glycol, 1/3 water, because that's where the eutectic is. And this really goes low, right, to minus 65 Celsius. So in most of Michigan, you're okay. But what you do when it gets colder, that's when people plug in their car, right? So, you know, like if you go to Alaska in the deep of winter, and in some parts of the US, people actually literally plug in their car to keep their radiator slightly heated while the car is parked. But I'll tell you a good story. You know, this is the kind of friends I had when I was young. So people go like, you know, oh, ethylene glycol, it stops your engine from freezing, so let's just use pure ethylene glycol. That must be better. So, but if you put pure ethylene glycol in your radiator, your melting point is only like minus 12 or something. So you will actually freeze your radiator. So melting points is one of these things that truly is nonlinear. And you have to, when you ever make your own antifreeze, which by the way is trivial, right? It's just 2/3, 1/3. And you put some colorant in so that you actually, because ethylene glycol is actually transparent, right? But if you buy it in the store, have you noticed how it looks green or blue? And that's because they put colorant in so that you wouldn't drink it. Although I'm not sure why that makes it you not drink it. But so the melting point of the mix is minus 62. Okay. I have one more fabulous phase diagram for you, which relates to an important issue is how to have the perfect cocktail party. But since that needs more time, I think I will do that next time. And it can wait since none of you have any cocktail parties anyway now, but hopefully soon again. So with that, let's end here, and I'll see you on Wednesday. Have a good week.